So I've transferred the data here to Excel. I've got X and Y, and we're just trying to create this simple linear regression. So the model we're trying to create is Y hat equals beta naught plus beta 1 times X. The first thing I'm going to do is just name a couple things. I'm going to name this little x, or I'll call this X data. I'm going to name this Y data, and these are vectors. So we have X data and Y data. And I want to emphasize the difference between little x, which is just a 4 by 1 here, it's a 4 by 1 vector, and capital X. Capital X, let me go back to this slide here, is composed of ones. It's always, the first column of capital X is always just a bunch of ones. And that's because if you look at the left hand, if you look at the first term of our system of equations over here, we're multiplying beta naught times 1. We don't have any functions of x. We don't have any x in there. So capital X will always be composed of a column of ones. And then in this case, we have x1, x2, x3, x4 in column 2. So that's the difference between capital X and little x. Little x would just be a vector of x1, x2, x3, and x4. So I've named this X data. I've named this Y data. And now we are ready to go about solving for beta. Now in order to solve for beta, we first need to calculate x, so big X. I'm going to put a label here for big X. And big X is just going to be 1, 1, 1, 1. So it's just a bunch of ones. Plus, we're going to add in the x, little x value. So I'm just going to do control copy and control paste. So this is big X. And I'm just going to name this capital X. So that's capital X. The next thing we need is we need to get XTX. XT is the transpose of X. So I'm going to put a label there for XT. The transpose of X is just swapping the rows and columns, making the rows equal to the columns and the columns equal to the rows. So this is a 4 by 2, 4 rows by 2 columns. The transpose then, we just swap the rows and columns, so 2 by 4. In Excel, you have to outline the region that you want to output. And in Excel, there is a transpose function. So I'm just going to do transpose of X. This is an array function. And because of that, you need to do Control, Shift, Enter. And now what we've done is we've transposed X. I'm going to go up here and name that XT for X transpose. The next thing we need to do is we need to take the inverse of XTX. But first we have to calculate XTX. XT has size 2 by 4. X has size 4 by 2. So if you take a 2 by 4 times a 4 by 2, you end up with a 2 by 2. So this is going to be XTX. I'm going to outline a 2 by 2 array. And there's a matrix multiplication function built into Excel. And that's going to be X times, or actually XT, because order matters. XT by X, Control, Shift, Enter, and that is XTX. Now we need to calculate XTX inverse. The inverse of an array always has the same size as the original. So the inverse of XTX will have the same size as XTX. So I'm just going to highlight a 2 by 2. There's a minverse, matrix inverse function built into Excel. And let me back up a step because I need to name this just to make things a little less confusing, XTX. And going back here, I have my 2 by 2 equals matrix inverse, minverse of XTX. Control, Shift, Enter. And that's the matrix inverse. The inverse of an array has a property that when you multiply the original array by its inverse, you get the identity array, which has ones in the diagonal elements and zeros elsewhere. We're getting there. All we need to do now are a couple more things. I'm going to calculate XTY. I'm going to go over here, XTY. XTY, XT has dimensions 2 by 4. Y has dimensions, Y is our Y data, 4 by 1. So when we multiply a 2 by 4 by a 4 by 1, we end up with a 2 by 1. So I'm going to highlight a 2 by 1, and this is going to be equal to m mult of xt by our y data. Control, Shift, Enter. That's XTY then. Now I've got XTY, I've got XTX inverse down here. So I can just finish this off with beta. The size of XTX inverse is a 2 by 2. The size of XTY is a 2 by 1. When we multiply a 2 by 2 times a 2 by 1, we end up with a 2 by 1. So beta is going to be a 2 by 1. And that's just going to equal then m molt. And actually, let me escape again here because I want to name this XTY. XTY. Beta is going to be equal to m molt XTXINV. Actually, I forgot to name that, but we can rename it here in a minute, times XTY. Control, Shift, Enter. And in order for that to work, I have to make sure I name this XTXINV. All right. So this is our beta vector, and this is the important conclusion. This is sort of what we're trying to find with this. That means, looking at our model here, y hat equals beta naught plus beta 1. This is our intercept, and this is our slope. There's a built-in intercept function, so we can do the intercept of our known y's and our known x's, and we get 1.5. So that's there's a built-in function, so that's just to check. And we can also use the slope function, known y's and known x's, and we get 1.76. These are the exact same values you would get using the regression tool in Excel. So the regression tool is actually using this technique. So in conclusion, going through this matrix approach, we can calculate the coefficients beta naught and beta 1 of our model here, and that ensures that we have the line of best fit in this case. I'm going to show you another example where we have a way more complicated function. We're going to have a function of a 5-parameter model where we're going to have a bunch of functions of x in the next screencast. Thanks for watching and hope you enjoyed.